So this session, we start with the relation between bandwidth and rise time for a practical filter. So uh, before starting this, just I want to recollect the uh, meaning of this rise time. Just I have a question. Does this rise time relates to input of the system or output of the system?
Output.
Yes, it is. So it is output. So uh, it is the time taken for the output to rise from how much percentage?
10%.
10% to 90%.
10% of maximum value to 90% of the maximum value of output. Okay, this is how we have defined the rise time. And also we have earlier seen what is the 3 dB bandwidth. So we start with a practical low pass filter, which I have considered is a simple RC circuit where X of t is the input and Y of t is the output. Just assume that I of t is the current passing through the circuit. Okay. Now, to observe this rise time, we have to give the input as a unit step so that which is constant over the entire time duration, which is given as an input. And output, obviously we find it as convolution between input and impulse response. Okay, so this is a practical low pass filter. Yes, this is all the recollection which we have already seen in the last class. Now, what we did next?
H of t cal.
Yes. So, to find the output y of t, we have to find h of t first because already you know x, input x. So, to find h of t is the first objective. So, to find h of t, what we do is we apply KVL for the input loop. So, applying the KVL in the input loop. So, x of t equal to r into I of t plus 1 by c integral I of t dt. Next, also apply the same in the output. That means the output y of t is always measured across the capacitor. Now, to get h of t, I need to find h of omega first. To make it to make the simplification easier, I'm going to find h of omega first. So h of omega, how can I get? It is the ratio of y of omega by x of omega. So to obtain y of omega, what should I do?
Fourier transform on both sides.
Right.
For
So
equation 2.
right. So applying Fourier transform for equation 2, you will get. So applying Fourier transform, you will get y of omega equal to. And here, I'm going to apply use the property of time integration of Fourier transform. Time integration property of Fourier transform. So it becomes 1 by c integral is replaced as per the property, it is 1 by j omega, and I of t becomes I of omega. So this is equation 3. Similarly, to find x of omega, we are applying the Fourier transform for 2 and 1 both. So that becomes r into I of omega plus 1 by c 1 by j omega into I of omega is a Fourier transform for this. This is equation 4. Now we can easily find this transfer function or frequency response by taking the ratio y to x. I'm going fast because this already we did in the classroom yesterday. Can anyone tell me the final expression?
1 by 1 plus j r omega c.
1 plus j omega rc. Okay. And from this, how can I get h of t?
1 by a plus j omega form.
Right. Applying the inverse Fourier transform to 5, or or you can recollect the form like 1 by a plus j omega. When you see 1 by a plus j omega form in the Fourier transform, it is understood that it is representing the Fourier transform of e power of minus at u of t. So this I am using now. So before that, I'll be writing h of omega in a proper form by dividing with rc, numerator and denominator. So 1 by rc by 1 by rc plus j omega. This I am writing it as 1 by rc times 1 by 1 by rc plus j omega. So now this is very similar to your 1 plus 1 by a plus j omega. Then what will be h of t?
1 by
1 by
r
rc
c
is the constant, right? And in place of a, what do you have in place of a? In place of a, you have 1 by rc, so e power of minus a into t u of t. This is how we can write it as 1 by rc e power of minus t by rc into u of t. Okay, and now output y of t of the practical low pass filter can be found by performing convolution between input and impulse response. And to make the simplification easier, and since the convolution satisfies the commutative property, I can also write h of t convolution x of t. Now what is x of t?
u of
U of t. And what is h of t? 1 by rc e power of minus t by rc into u of t. Now let's go for applying the convolution formula. So writing the convolution formula of infinite limits and writing the formula for this part. It means h of tau x of t minus tau deta. Now please substitute what is h and what is x. 1 by rc e power of minus. What should I write? You can respond.
minus tau by RC.
Right. So you have already you have h of t here. Okay. Just you have to represent that as h as a function of tau. That means simply replace wherever you have t, replace with tau. So minus tau by rc into u of tau multiplied with. What is x of t? It is u of t. Now what should I write for x of t minus tau?
u of t minus tau.
U of t minus tau plus theta. Now we have to properly understand like how the limits will change. So for that, what I'm doing is I'm concentrating on u of tau and u of t minus tau. Now let me plot u of tau first. So tau, u of tau. Is this correct what I have plotted?
Yes,
Yes.
sir.
Right. Now, uh, instead of directly plotting this u of t minus tau, what I'll do is, as discussed in the lab when we were doing the convolution operation, first I will represent u of minus tau, then I'll be plotting u of t minus tau. So what is u of minus tau? Is it the time reversed version?
Yes, sir.
Yes. So u of tau, u of minus tau is the time reversed version of u of tau. Right. Then I have a question now. X of if I perform x of t minus 1 for suppose, this is representing delay. Uh, what is the direction of shift, right or left?
Right.
Right.
Correct. X of t plus 1, it is advanced, right?
Advanced.
So advanced means it is shift towards left. Now tell me again, if I have x of minus t, then what will be this x of minus t plus 1? Shift towards right or left?
Right.
Right. So it is shift towards right. Whereas x of minus t minus 1, because of this negative sign, the direction reverses. So it should be shift towards left. Okay. Now, why I am discussing all these means, in the formula you have u of t minus tau, that can be represented as u of minus tau plus t, where u of minus tau is the time reversed version and t is the amount of shift. Now just try to correlate these two. These two are in the same form. Am I right? Instead of tau you have t, and instead of t you have 1. That means this signal after time reversal should be shifted right side by how many number of units? After time reversal,
T.
uh,
T unit.
you have to shift by t units towards right side. Right. So I am now redrawing this u of minus tau. Again, I'm redrawing it. This is time reversed. And after that, I'm trying to plot u of minus tau plus t, or as you wrote in the formula, u of t minus tau, whatever it is. Now it is a shift towards right. Am I right? By how many units it has to shift?
T units.
T units. That's why earlier it was 0. Now it is shifted by t. That's why it is t. And this amplitude is 1, the same. Now, please tell me, for this signal u of t minus tau, what will be the time limits? For this, what will be the time limits? Tell me.
Minus infinity to T.
Right, exactly. Minus infinite till t you will get. So time limits will be minus infinite to t. Now, going back, what will be the limits for this u of tau?
0 to
Zero infinite.
infinite.
Nice. So time limits will be from 0 to infinite. Why I am talking all this is because the limits of this integral should be properly defined based on these two functions because they are well defined, u of tau and u of t minus tau. U of tau, the limits are 0 to infinity. U of t minus tau, the limits are minus infinity to t. So I am rewriting here. U of tau, the limits are from so 0 to infinity. So maybe I can redraw that again. u of tau. This is 1, 0. Now, in the formula, after substitution, we see that like it is a product of u of tau and u of t minus tau, where you can see both here, u of tau and u of t minus tau. Now tell me, what is the common limit in which the product exists?
0 to
0 to t.
0 to t. Excellent. So the product of u of tau and u of t minus tau exists in the time limits. The common time interval where the product exists is 0 to t. That's why here the limits now will be modified from 0 to t. So let's evaluate the output of the system. So y of t equal to 1 by RC integral. Now the limits will change from 0 to t. This is how we get the limits. Next, the functions are as usual e power of minus tau by RC. And what is the value of u of tau? What is the value of u of tau
1.
in this range?
1.
1.
1, right? And what is the value of u of t minus tau in this range?
1.
1, right? So both the functions are unit step. That's why these values becomes 1. And finally, so you have 1 and 1 theta. So 1 by RC integral 0 to t e power of minus tau by RC theta. Please evaluate this 1 by RC e power of minus tau by RC by minus 1 by RC. Am I right? After integration. And you have to apply the limits 0 to t. Now, can I cancel this 1 by RC?
Yes, sir.
So you don't have 1 by RC, but please make sure that you don't leave this minus. Okay, minus exists. So it is y of t equal to 1 by RC. Sorry, 1 by RC. So y of t equal to minus e power of minus tau by RC with the limits of 0 to t. Apply the limits and write the result. Apply the limit, you observe minus e power of minus t by RC minus of minus plus e power of 0 is 1. So finally, the output y of t is 1 minus e power of minus t by RC. And and this result exists. See the time limits now. All these result exists from 0 to t, right? Always. Am I
Yes,
right
sir.
or wrong? Okay. So therefore, this result is always exists for t greater than 0. Till this point, it is clear.
Yes, sir.
Yeah. Now after this, we have to calculate the rise time. Now before that, I want to have a plot for this. So if I go for a plot for this, e power of minus t by RC. How will be the plot? Anyone? I'm not asking for 1 minus e power of minus t by RC, but I'm asking for e power of minus t by RC. Is it a decaying exponential or a growing exponential?
Decaying exponential.
Decay, because we have a minus sign. So e power of minus t by RC will be like this. It decays. where it starts. Okay. Now, this is not the actual output. What is the actual output? Actual output y of t is 1 minus e power of minus t by rc. The proof for t greater than 0. Then how will be the plot? How will be the plot? Before subtracting this from 1, what is the maximum value you got here?
1.
1.
1, right? Now, when I subtract this from 1, what happens to the value at t equal to 0?
It becomes 0.
0. That means the response starts from the origin. That is half, you get a rise, exponential rise like this. It starts from 0. Now, at what value it settles? Because the output exists for t greater than 0. The maximum limit that t can take is infinity. And if I substitute in place of this t as infinity, it becomes e power of minus infinity. What is the value of e power of minus infinity?
0.
0. That means the maximum value the signal it reaches is
1.
1. This line, this dashed line I have drawn to make you understand that the signal output y of t, the system output y of t, reaches a maximum value of 1. And that touches 1 only at infinity. Okay. Now, let me mark. What is the maximum value? Tell me.
1.
1. Okay. So I am going to the top, that is to the definition of rise time. The time taken for the output of the system to rise from 10% of its maximum value to 90% of the maximum value. Okay. Now, the maximum value is 1. What is 10% of 1?
0.1.
0.1 becomes a 10% of 1. 10% of maximum. And what is 90% of maximum?
0.9.
0.9.
0.9. So this becomes 90% of maximum. Okay. So what now I am doing is I am extending this onto the output. It touches here. Extending this onto the output touches here. So this is the time t1 at which the output is 10% of the maximum value. And this is the time t2 where the output has reached 90% of the maximum value. So tell me what is the rise time now?
T2 minus T1.
Right. So TR equal to T2 minus T1. Okay. Now let's evaluate this based on the plot. At what time the output is 10% of maximum? Tell me.
T1.
Right. So at t equal to T1, I am going to evaluate the output y of T1 using this equation. Substitute wherever you have t, you have to replace with T1 equal to 1 minus e power of minus T1 by RC. And what is the value at t equal to T1?
0.1.
0.1. So that should be equal to 0.1. So from this, what I am doing is I am trying to calculate T1. So that's why I'll take this e power of T1 by RC onto the right side and bring that 0.1 onto the left side. Understood?
Yes, sir.
Okay. So 1 minus 0.1 is 0.9. That equal to e power of minus T1 by RC. From this, I want to calculate T1. So I'll be applying the natural logarithm on both sides. So when I apply the natural logarithm, minus T1 by RC is equal to natural logarithm of 0.9. Can anyone please calculate the value of natural logarithm of 0.9 in your calculator? I also have, but please do from your side also.
Minus 0.0457.
Natural logarithm, not log 10, it is ln. ln of 0.9.
Minus 0.10536.
Right. So minus T1 by RC equal to minus 0.1053. Okay. And from this, you can remove the minus. Samiksha, please admit somebody is trying to. Okay. And then what is T1 from this?
0.1053 RC.
Okay. Right. Uh, let me write this. Let me highlight this. Next, similarly, can you find T2? What should I do? Just substitute at T equal to T2. What happens to output? In this, substitute T equal to T2. At T equal to T2, what is the output?
0.9.
Right. Earlier, we have equated to 0.1 at T1. Now, we'll be equating that to 0.9 at T2 because it is 90% of the maximum. Okay. So, do the same. So, 1 minus e power of minus, you can proceed equal to 0.9. Similarly, the same, whatever I did earlier, I am writing here. So, e power of minus T2 by RC will be equal to 1 minus 0.9, which will be equal to 0.1. And from this, I want to find T2. So, I am applying the natural logarithm. Please tell me the value of natural logarithm of 0.1.
Minus
Minus 2.30.
2.3027.
Right. So, minus T2 by RC equal to minus 2.3026.
6.
Okay. So, you can cancel minus. You can remove minus. And finally, T2 can be written as 2.3026. Okay. Now, finally, not finally, but we have now come to a conclusion about the rise time. It is T2 minus T1. Please tell me what is T2 minus T1?
2.197.
RC minus 0. How much it is? 0.1053 RC. 1053 RC. How much it is?
2.1973 RC.
2.1973 RC. Okay. So, sorry, not T2, it is TR. It is TR. So, 1973, I'm approximating to 2.2. Okay. Just approximate. Till now, what we did, just I'm recollecting once again. We understood the definition of RC, just recollected the definition. Output should rise from 10% to 90% of the maximum value. Why we are leaving this 10% at the beginning and 10% at the end?
Because of noise present.
Because there may be a presence of noise to eliminate that ripple behavior or variations in the output. So we are going for reducing that. So we consider this practical LPF, low pass filter, applied the unit step signal. And for an LTI system, output is X of t convolution H of t. So that's the reason we are trying to, because we know X of t, we are finding H of t. So from the system information, we found the transfer function. It is 1 by 1 plus j omega RC. Writing it in a proper form, we found the impulse response h of t. Then we found the output by performing the convolution, and here commutative property is being applied so that I can make the simplification easier. Then after redefining the proper limits, we have evaluated the output, and it is 1 minus e power of minus t by rc. And since the integration is evaluated from 0 to t, from 0 till any value of t, that's why output is defined for t greater than 0. This is the plot is e power of minus t by rc only, which is a decaying exponential. But the output is 1 minus, that is how you get a rise from 0 to a maximum level of 1. Therefore, next we marked the maximum value is 1. That's why 10% of maximum is 0.1, 90% of maximum is 0.9, and the time limits t2 minus t1 gives the rise time. And since we know the values of maximum and 10% of maximum and 90% of maximum, therefore we have found t1 and t2. It is t1 is 0.1053 rc and t2 is 2.3026 rc, and finally t2 minus t1 gives the rise time, it is 2.2 rc. Now, till now we have discussed only about the rise time. And what is the objective here? It is a relation between bandwidth and rise time. So now we have to discuss about bandwidth of the system which we have considered. So now I am talking about bandwidth of the practical low pass filter. Okay. So if you see the practical low pass filter, right? So this is a simple RC circuit that what we have considered as a simple RC circuit, which is a practical low pass filter. Now, can anyone recollect what is a 3 dB bandwidth means? Three dB bandwidth. Anyone? Am I audible?
Yes.
3 dB bandwidth. What are these 2 points which I have marked on the magnitude response?
Higher frequency and lower frequency.
Right. So these are the two frequencies, F1 and F2, at which the magnitude is 3 dB less than the maximum. Am I right?
Yes, sir.
Yes, sir.
This is what we say it as 3 dB bandwidth, which I am writing it as F3 dB. Just this is a recollection of what is 3 dB bandwidth. Now, since this is a dB graph, just I want to also show a normal graph. Maximum value will be 1 and zero point 1 by root 2 or 0.707 times the maximum. This is what we consider on the direct value of the gain curve. Audio frequency. Okay. Therefore, omega, whatever you can write, no problem. In case if I write in terms of F, it becomes directly f3dB. In case if I write here, this becomes omega 3. Then we can write in terms of like getting 2 pi. Now tell me, so at these frequency values, what will be the magnitude? It is 1 by root 2 times the maximum. Am I right?
Yes, sir.
Now please tell me what is h of omega you have got. Is this correct? Which I wrote here?
Yes, sir.
Okay. Now, since we need to find the magnitude, what should I do? I need to go for applying the modulus for h of. And it is very simple that because we only have the complex term in the denominator, it is 1 by root over 1 plus real part square plus imaginary part square. Real part is 1, imaginary part is omega square r space t square. Understood?
Yes, sir.
Yeah, just I wrote mod h of. Now, at omega equal to 0, you will get the maximum. Am I right? You will get the maximum. And what is the maximum value?
1.
Right. This is only for the diagram purpose. Okay. Don't match this with the filter. This is only for recollecting the definition of the dB band. Okay. Now, to get the 3 dB bandwidth, this should be equal to what value? Tell me the magnitude. I am giving the clue here. The magnitude should be equal to what value?
0.707 of maximum.
Right. Okay. So maximum is 1. You can write 1 by root 2 even. No, because already you have 1 by root over 1 plus omega square r square c square. So we have to go for 1 by root 2. So equate that to 1 by root 2. Okay. So I'm removing this question mark now. Then at that value of omega 3 dB, the magnitude should be equal to 1 by root 2. Now, please simplify this. Squaring on both sides, what will you get? Because already you have both 1 by root and 1 by root. I'm directly writing like this. Will you accept it or not? Please tell me.
Yes, sir.
Is it okay?
Yes, sir.
Yes, sir.
Right. So at omega equal to omega 3 dB, the magnitude should be equal to 1 by root 2. And from this, can you please find f3 dB? Please do it on your side. I am also doing. 2 minus 1 becomes 1. And omega 3 dB square is equal to 1 by RC whole square. Frequencies will be positive, so don't take minus. So omega 3 dB equal to 1 by RC. But we don't need omega 3 dB, we need f3 dB. So omega is 2 pi f, that's why I'm writing as 2 pi f3 dB equal to 1 by RC. And finally, the 3 dB bandwidth will be 1 by 2 pi RC. Is it clear?
Yes, sir.
Okay. So now you have a relation for 3 dB bandwidth, and you also have a relation here for rise time. So it is approximately 2.2 RC. So I am again recollecting rise time is equal to TR equal to 2.2 RC. Now from these two, can you please eliminate RC and get the relation? Two point two from this you can write RC is 1 people, and in case of this RC, will be replacing it 1 by 2 pi f. Please tell me what is this 2.2 by 2 pi? Two point two divided by 2 pi. Please tell me the value.
0.35.
0.35. 0.35 by 10 3. Earlier, when we are seeing the relation between bandwidth and rise time for ideal low pass filter, what did you get?
1 by F3 dB.
1 by f3 dB, right? That is, it is indicating that the rise time is inversely proportional to f3 dB. Here also, we observe that rise time is inversely proportional to f3 dB. The only thing is that the constant factor, whatever we have here, that is the proportionality constant factor, will change depending on the type of filter we are using. That means the result is same. The only thing is the proportionality constant factor will change. That's it. Okay? Is it okay?
Yes.
So the conclusion is rise time will be always inversely proportional to the 3 dB band. This is what the conclusion we draw from.